the webinar. Good morning, everybody, and welcome to today's Celsius talk. My name is Sarah Johnstone, and I'll be moderating today's webinar, which will explore the issue of how heat and power interact and interrelate in district energy systems. As both power sources and district heating and cooling networks evolve, making the most of synergies is one of district heating's significant advantages. But with integration comes the need for technical and market solutions, which we will delve into today. So during this online meeting, we will first hear from Jens Kuhne of AGFW, who will give us a rich overview of the relationship between power and district energy systems. Andre David from Aalborg University will then explore the important role of large-scale heat pumps in district heating, before we move on to the presentation from Eftim Popovsky of Fraunhofer ISI, who will draw on a case from the Progress Heat project to discuss heat pumps from a cost-effectiveness perspective. We will then hear from Jay Hennessy from RISE, looking forward to the future role of thermal grids, and finally from Håkan Andersson and Magnus Karlström of Skanska, who will discuss the ever-important topic of thermal energy storage. Time allowing, we will finish with a Q&A. So let's move straight on to the first presentation. Jens Kuhne is a consultant for heat generation and CHP at AGFW, the Energy Efficiency Association for Heating, Cooling and CHP based in Germany. Jens holds a PhD in mechanical engineering and several years of research experience. His current role is focused on large and medium heat generation facilities and thermal storage in district heating systems. Jens, the floor is yours.
Okay, thank you, Sarah, for the introduction. Good morning, everyone. Today I will do the start of this interesting webinar, and within the next 10 minutes I will give you an overview and insight on the experiences and the challenges in Germany that are connected to the thermodynamically irrational transformation of electricity into low-temperature district heat, what we call power to heat or power to district heat. Let me first start with our definition of the term as power to heat. When we talk about it, we will think of a large-scale and central transformation of electric power into district heating. This application is integrated in a multivalent heat generation portfolio, where preferably a combined heat and power plant is the major heat generator. Normally, there are two technologies for power to heat: an electric flow heater, which is basically used for electric capacities up to 15 megawatts, or electrode boilers that are used in ranges from 10 megawatt and upwards. In addition, there are also large-scale heat pumps that have to be taken into account, and where we'll hear more about in the following talks. On this map and the regarding table, you can see the already installed municipally operated power to heat applications in Germany that add up to about 350 megawatts in total. The capacities of the single applications range from half a megawatt up to 30 and 50 megawatt. What you can also see is a nice distribution over the whole area of Germany. But when it comes to an economic rating of applications and potentials of power to heat in Germany, the depicted diagram shows three different areas of possible operations over the timeline. Starting with Area 1, where power to heat applications are utilized for provision of balancing power, followed by Area 2, in which power to heat helps to stabilize the electricity grid in cases of regional or local surplus energy from renewables that are destabilizing the grid. And for a long-term view in Area 3, the operation of power to heat that provides sector coupling between the electricity grid and the heat market in times when surplus energy from renewables is present in the whole market range. The first two areas are already in action, and we are working on the political framework for the third area right now. But let me describe the basics of all three areas briefly within the rest of my talk. Balancing power helps to stabilize the frequency of an electricity grid in case of a lack of balance of electricity production and demand. Therefore, you can offer a generation unit or an electricity sink in order to stabilize the balance again. The balancing power market in Germany is divided in three different products: primary, secondary, and minute reserve, which follows each other in a cascade. The most interesting product for offering power to heat as an electricity sink is the secondary balancing power. As a basic requirement, you need to start up your power to heat application within 30 seconds, which is feasible for the described technologies. Taking a look at the picture at the bottom of the slide, you can see the different developments of prices that can be earned by operating power to heat within the secondary balancing power market over the last 5 years. There are three different graphs. The blue one describes the average demand rate, a price that can be earned by only providing capacity in euro per megawatt and week. The green and the red graph depict the development of the average working price that is paid for the physical operation of secondary balancing power in off-peak times in red and peak times in green in euro per megawatt hour. Looking at the blue graph, you can see why all the listed companies have started to invest in power to heat in the years 2012 to 2014 in Germany, where we could see prices of about 1800 euro per megawatt and week without operating it. But after these years, the demand rate prices decreased enormously down to a value of almost zero. When in this time, the working price instead for secondary balancing power rose from almost zero to about 3,500 euro per megawatt hour. This sounds interesting, but you have to take into account that the operation times in this market are often limited to just a few seconds. So the economic potential for power to heat in this market sector has decreased, or better, has almost died. When we come to the second area, we have to analyze the German energy transition in this context. Within the last years, Germany had a vast growth of renewable energies like wind and solar power. The fluctuating feed-in of electricity of these applications, combined with an areal disbalance, for example very much wind farms in the north, lead to destabilizing of the electricity grid. In order to avoid destabilized grids, there are different regulative measures, so-called redispatch and feed-in management. Application of both measures have vastly increased within the last years, combined with a vast increase of costs. A vast increase of costs that added up in 2015 in almost 1 billion euro, with a still increasing tendency. In order to avoid rising costs, two different measures have been invented. First, the so-called use instead shutdown measure, and secondly, an experimental clause for future application of power to heat, so-called Syntec. The first measure is a contractual agreement between the electricity grid operator and an operator of a combined heat and power plant. The agreement is about a process that the grid operator can shut down the CHP in order to stabilize the grid in cases of high renewable feed-in. By shutting down the CHP, he is bound to provide electricity for the operation of power to heat for free. In addition, the grid operator also pays the investment costs for the installation of the power to heat application. But there are also disadvantages in the nice sounding measure. The CHP is also earning money from different sources beside electricity feed-in and heat generation. You can, for example, also provide system services. The question that rises is, how can the grid operator pay an adequate reward for shutting down the CHP? In addition, there are also questions about a parallel market option of the CHP and the installed power to heat and the consideration of the electricity in terms of primary energy factors. The second measure I mentioned is to avoid rising costs for stabilized electricity grids. It is the so-called SynTech project, which is an R&D project that should focus on digitalization of the energy transition and also includes sub-projects of an intelligent operation of power to heat in the future energy markets. In total, there are subsidies of 200 million euro over the next 4 years. The goal of that project is the real sector coupling of electricity, heat and transportation markets, the stabilization effects of power to heat on the electricity grid, and the effects of less regulatory electricity price components. These price components is also the key word for my last slide that covers region 3 in my diagram at the beginning. The stabilization of the electricity grid and utilization of electricity in times of a market-wide surplus of renewable electricity. Our offer is that our power-to-heat applications can utilize the renewable electricity by coupling the electricity and the heat market, and hence brings more renewables in the district heating system. Before that can be realized, we have to overcome a large hurdle characterized by the regulatory framework. The major drawback is the electricity price due to regulatory price components. On the right picture, you can see the relation between the market price for electricity in blue, here the average of 30 euro per megawatt hour, and all price components that are added. For example, in orange, the EEG reallocation charge that has to be paid for the subsidies of renewable energies, the grid fee, or the electricity tax. Altogether, we end up at an electricity price of more than 150 euro per megawatt hour compared to a market price of 30 euro per megawatt hour. In the diagram at the bottom, you can see that the economic feasibility of a power-to-heat operation with the real electricity prices is not given as long as the regulatory price components have to be paid. Right now, we are working on that political field in order to create a framework that enables a stabilizing, intelligent, and forward-looking sector coupling with power-to-district heat. Coming to my conclusion, over the past few years, power-to-heat has successfully been operated with the electricity balancing market in order to integrate renewable energy sources. The profits have decreased in the past 2 years, which makes it not a feasible market option for power-to-heat applications anymore. For the stabilization of the electricity grid, 2 new instruments are on their way. The success of both instruments have to be proven over the coming years. And for a feasible coupling of the electricity and the heat market by power-to-heat, the regulatory framework has to be rearranged. The focus has to be laid on the regulatory electricity price components that are added on the market price for electricity. Yeah, thank you for your attention. And yeah, the floor is open, I think, for the next presenter.
Okay, thank you very much, Jens. Just before we move on, is there anyone listening that has a direct question for Jens following his presentation? We will have another chance at the end of the webinar to ask all of the speakers questions as well. While you sit and think about what you might like to ask, either now or at the end, I have a question or reflection based on the presentation we have just heard. You talked towards the end of your presentation about using surplus renewable energy in power to district heat. How high is the probability of changes in the regulatory framework here?
That's a good question, because we are working on that field since the last 3 years, and in that framework, the projects or the measures I introduced were already being implemented, and so we are thinking over the next few years we can see changes in this regulatory framework, and we are still optimistic that parts of these price components can be changed or avoided for the use of power to heat applications. So we are still optimistic and still working on it.
Okay, thank you for that. And just one follow-up question as well. You talked about 2 measurements for stabilizing the electricity grid. I think it was use instead, shutdown, and Synteg. What has the response been like to these measurements?
Yeah, so the response is, for the Synteg R&D project, the response is very high. So we have nice projects that are already on their work and try to start with their application of power to heat and also their operating. And on the other hand, this other measurement, this use instead of shutdown, it's not as nice or as successfully started as the Synteg project, because they're all, since we still have some problems or risks for the operators that are not solved yet. So I don't think we have, I think we don't have any agreement yet, and I think we will have to wait some more months in order to find some people that are agree on a contract.
Okay, well, we would love to hear the follow-up once you have that.
Yeah, I'm also interested in.
All right, thank you very much, Jens. I will now move on to our next presenter, Andre David. Andre holds a master's degree in sustainable cities from Aalborg University, where he is currently employed as a research assistant with the Sustainable Energy Research Group. He's also a contributor to our Celsius City Supporter project, Heat Roadmap Europe, and has particular expertise in the area of heat pumps and their relationship to district energy systems. So, Andre, the floor is yours.
Thank you, Sarah, for the introduction, and hello, everybody. Since the time is short, I will go straight ahead into presenting my part. And I will start with an introduction of what is the role of heat pumps in the future energy systems. As you can see from this graph, heat pumps are expected to have quite a central role in the future energy system, working in collaboration with renewable energy production, such as wind or solar, but also in a close partnership with combined heat and power systems. On the demand side, the heat pumps are expected to produce the heating and cooling demands, but also function in close collaboration with thermal storage when needed. Another connection, which is not shown in this graph, but is very important for the future, is the connection of the heat pumps with various industrial sources which provide excess heat. So that provides an additional connection of that heat pumps can provide with other sectors than the ones presented in this graph. In the future, heat pumps are expected to function when the wind production or the RES production is higher and the electricity prices are lower, to provide the heating demands and also use the thermal storage when needed. In terms of low RES production, low wind production, for example, or low solar production, the combined heat and power systems can supply the electricity and the heating demands. In the future district heating systems, large-scale heat pumps are expected to function function well in the fourth generation district heating systems. That is because there will be more accent put on the power to heat solutions, but also because the temperatures in such a district heating system will be lower, approximately 50 to 60 degrees Celsius, which makes a better case for larger scale heat pumps because they can have a higher efficiency. Heat pumps can come in sizes of several megawatts as centralized heat pumps, but can also work in connection with other heat production units, such as the large-scale solar or geothermal, or even the industry, as I mentioned earlier. But in order to understand how these heat pumps can actually function in a fourth-generation district heating system, we also need to look a bit into the current situation, also a bit into the past, and see what's the status of the technology in the third generation of district heating, how this technology has evolved over time, and if it's available and ready to be used in a fourth generation district heating. To do so, a review on the status of technology has been made as part of the HydroMap Europe studies, which is a survey on the status of this technology, looking into the heat pumps with a thermal output capacity of at least 1 megawatt thermal. According to the study, the technology is in use since the 1980s in Sweden, and today the capacities have reached approximately 1,600 megawatts across Europe. As it is shown in the graph on the right, the average capacity of the heat pumps has changed over time. If in the 1980s and 1990s the capacity was between 12 and 19 megawatts on average, nowadays the capacities of heat pumps average approximately 3 megawatts. The graph on the bottom shows the age of these heat pumps and a distribution on the countries. Sweden still has a very large capacity, much higher than the rest of the countries, but most of the heat pumps are pretty old, I would say, over 30 years old in some cases, in many cases. But the capacity in Sweden was even larger, where there were approximately 1,500 megawatts of capacity installed, but in the past years, approximately 300 megawatts have been decommissioned. However, in the other countries, the heat pumps are newer, and of course, they have a longer lifetime than the ones in Sweden. Going further, in terms of heat sources, the survey identified multiple heat sources. But among these heat sources that you can find on the table on the bottom, 3 heat sources stand out, and that would be sewage water, ambient water, which is the sea, river, or lake water, but also industrial waste heat. Now, out of these 3 heat sources, since the time is limited and I cannot talk about each of them in particular, sewage water presents the best characteristics, and as you can see from the graph on the bottom, it has also the largest capacities nowadays. That is because sewage water has 3 advantages. First advantage is that it provides rather high heat source temperatures between 10 and 20 degrees Celsius. It is found generally in the proximity of urban areas, which presents a better case for the investment and for the connection to the district heating system. And also it has the benefit of having the long-term stability, meaning this heat source has a low risk of being decommissioned in the next years, meaning it's there to stay. And it is very important to mention, because the investments in energy are long-term investments. For example, in the case of industrial waste heat, there is a higher risk of this heat source to be decommissioned at some point in the future. I'm not saying that will happen, but there is a higher risk, and this has been demonstrated in another study on the status of heat pumps in Sweden, where the largest capacity decommissioned so far used as a heat source industrial waste heat. Going further on the refrigerants, the heat pumps nowadays use the hydrofluorocarbons, which are refrigerants with a high global warming potential. These refrigerants have been phased out, or they are due to be phased out by 2040, according to the latest meeting on the parties, meeting of parties. I'm not sure exactly if this is the right one, but it has been agreed to be phased down by 2040. And this is also the refrigerant used by these heat pumps. But alternatives exist. There are the natural refrigerants, mainly ammonia, which has at least 23 heat pumps installed nowadays with capacities over 1 megawatt. There's also the CO2 as a refrigerant, but that presents some issues in terms of capacity as it functions at higher pressures. And there's also the hydrofluoroolefins, the HFOs, which could represent another solution for the future. But these refrigerants are not accepted in all the countries and by all the stakeholders because they do not have the global warming potential as the hydrofluorocarbons, but once they get into the atmosphere, they decompose into some substances which can cause some hazardous effects. Nevertheless, in terms of temperatures, so the temperatures achieved by the heat pumps, even by the ones installed in the 1980s, are rather high and can supply the temperatures of 70 or 80 degrees in the district heating systems, and that is without compromising the COP. The graph shows that the COP is generally above 3 in all the cases for all the heat pumps that we managed to find in this survey. The heat pump operation is also a very critical part of in the future operation of heat pumps. That is because there are differences in how the heat pumps are operated. In Sweden, all heat pumps have been operated approximately 4,000 hours per year, while the newest heat pumps are currently operated 7,000 to 8,000 hours a year. And that is very important to mention because this is closely connected to the component wear, the mechanical wear of the heat pumps. There are examples of heat pumps in Sweden, specifically the heat pump in Gothenburg, which has been operated since 1990 strictly in connection to electricity prices, and there were no component failures, no mechanical failures because of this type of operation. So that shows it is possible to use the heat pumps in this way. However, other reviews have shown that there are some issues with the mechanical components if the heat pumps are used on a stop and start basis. Of course, heat pumps are dependent on the electricity prices and the biomass prices, but they have the advantage of displacing production from more expensive units, as it has been shown in different studies on the integration of large-scale heat pumps in Copenhagen, in a district heating system of Copenhagen by 2030. The same study also shows that the type of reconnection is very important in the sense that if the heat pumps are connected to the distribution grid, then they can have a higher COP because of the lower temperatures they have to supply, but they can only supply a limited area. Whilst if they're connected to the transmission grid, in that case, they can supply a larger area, but on the downside, they have a lower COP. This being said, the study we did at Aalborg University identifies some barriers for implementing more large-scale heat pumps in the future, and some of the barriers are the carbon penalty. Like the energy markets do not have a carbon penalty, and also they are still offering the subsidies are still offered for biomass and fossil fuels. We also identify some unwillingness of the policymakers to promote heat pumps, and they choose to stay technology neutral. There's also high investment costs for the heat pumps compared to the competing technology. But more importantly, there is a lack of knowledge on the technology maturity. And this is the aim of this study and also of this webinar, to show that basically the heat pumps have reached a mature technological level, and they have the capacity to be expanded to other district heating networks, because they can achieve high temperatures. There are alternatives for refrigerants, various types of refrigerants, and there is also a high availability of heat sources. So from all these points of view and more, the technology is ready for the future. But that is all I prepared for today. If you have any more questions, I'll be happy to answer, and thank you for your attention.
Thank you very much, Andre, for that interesting and comprehensive presentation. Again, I will ask if there is anybody in the audience that has an immediate question for Andre. If so, enter it into the chat. But in the meantime, Andre, I think it was you talked about a range of factors that can influence what kind of effects you get from integrating the large-scale heat pumps. Everything from the modernity of the technology, heat sources, the type of refrigerant you use, type of grid connection. Based on your survey, is there kind of one combination of solutions that you think would be sort of most implementable, most useful compared to others, or does it really have to depend on the local context?
Well, the implementation of heat pumps is very dependent on the local context, since the heat pump, well, first of all, it needs to have a district heating network around, which is not the cases of all the cities in Europe.
Yes.
But it is very dependent also on the availability of the heat sources. In general, we have found, and for example, a study done for Denmark has shown that pretty much all the cities in Denmark, 98%, they have a possibility of using of heat source for a heat pump. So from a heat source perspective, I don't think there will be major issues. The heat pumps, they don't have to supply the entire heat demand, but maybe even they supply a part of the heat demand. That is still a big achievement. Also, another important factor is the use of refrigerants, which has kept heat pumps away for being deployed on a larger scale, and could be a factor for the future. But it has to be understood that even though all the refrigerants, the hydrofluorocarbons, will be phased out in the next years, there are alternatives, and mainly the ammonia refrigerant. The best example is the heat pump in Norway, in Drammen, which has the largest ammonia heat pump units. Approximately, I think it's 4 megawatts per unit, and capacities of 6 megawatts can be achieved in the future, according to our knowledge so far. So, yes, what can I say more on this? There is a combination of factors, but it's dependent on the local situation. But technology-wise, I would say we are ready for having more heat pumps.
And that's a very strong message. So thank you very much for making it.
Thank you.
We'll now move on to our next speaker, Eftim Popovsky. He holds a master's in mechanical engineering, where his thesis focused on assessing technical options for renewable and energy-efficient heating and cooling supply in a city district. Since May last year, he has been working as a research assistant and associate for the Fraunhofer Institute for Systems and Innovation Research, where his focus areas include modeling district heating and cooling networks and retrofitting costs for building systems. He's a contributor to the Celsius City Supporter projects Heat Roadmap Europe and Progress Heat, which he will talk a little bit more about today. Take it away, Eftim.
Okay, thank you very much, Sarah, for the introduction, and good morning from my side as well. Today I will continue discussing the cost effectiveness of large-scale heat pumps, particularly for a specific case study in Germany. As part of the Progress Heat project, as you mentioned before, there were 6 different local case studies, one of which was the city of Herten, which is located in the North Rhine-Westphalen region in Germany. And today I will be discussing part of the results that were obtained as part of the Progress Heat project. Initially, I will be discussing a little bit about the district heating network in Germany so that we can see what are the challenges actually about integrating heat pumps into the existing district heating networks. Then I will say a couple of words about the city of Herten, what are the research questions, methodology and assumptions that we have taken as part of the research, and of course I will present the results and conclusions that are coming out of them. So first of all, just a few words about the district heating network in Germany. Even though in absolute values it is the largest network in Europe, as seen from the market share, we can see that it has around 13% of market share, which is quite lower than in comparison Denmark or Sweden. Then the average price, it's around 70 euros per megawatt hour, and we are still in that, let's say, third generation district heating phase with working temperatures of around 160 degrees Celsius. And based on the energy carriers, we can see that many district heating networks are still supplied mostly by coal and natural gas, of course followed up by waste and biomass as well. So in a way, the heat pumps have quite a competitor in the fossil fuels in this case. So what is typical about the city of Herten? It is that the district heating network is separated in 2 different parts, a northern and southern part, both of which are currently supplied by existing coal-fired CHP power plants, which are not part of the district heating network itself, and they are operated by another companies which are also supplying heat for several other municipalities. There are existing heat exchangers between the transmission pipelines and in the city district, which gives us a possibility of fully or partially decoupling some of the districts. For example, the city center of Herten, which is the largest district, and was the district that we have a closer look on it. And also, what is typical about the region, which is a former coal mining region, there's a lot of pit water that has to be pumped out every year, and this pit water has a temperature of around 20 degrees Celsius, which can, of course, be utilized as a heat source for the heat pumps. So, what were our research questions? Of course, first, as seen from Andrei's presentation, why are there no large-scale heat pumps currently integrated into the district heating networks? Are there technical or maybe economical reasons? And the second question was, of course, how to make large-scale heat pumps competitive. As far as of methodology and assumptions are concerned, we have, of course, started with certain cost assumptions, followed by technical assumptions, and the methodology was, let's say, quite simple. We have used energy simulation software, which was used for our simulation of the heat generation mix, so that we actually integrated in the existing coal-fired CHP power plants additional solar thermal collectors and heat pumps as well. And of course, we have analyzed the results in order to see how the system reacts with this heat generation mix. As far as the cost assumptions are concerned, we did not consider the size cost dependency, and in a way we have assumed a very high conservative specific investment cost of around 1,500 euros per kilowatt for all sizes of heat pumps that we have evaluated. The electricity prices that was considered is for a consumer with quite a large annual consumption of around 24 gigawatt hours. and the interest rates and taxes are from a private perspective. So in a way, we have evaluated let's say the business case of the heat pump in this situation. About the technical data, the heat pump provides heat up to 80 degrees Celsius, whereas the remaining part is covered by the existing coal-fired CHP power plant. As mentioned before, when the temperature goes below 0 degree, the temperatures in the network are higher. In this case, the heat pump cannot serve the district heating network, which points out the fact that we still have to conduct the transition from third to fourth generation district heating networks. And based on the heat pump efficiency and the temperature networks of the temperatures of the heat source and the district heating network, we have obtained by using Energy Pro an average annual COP of around 3, which was expected from our side, and shows that the software actually works in a proper manner. And in the next step, we have taken the city, one of the districts in Herten, which is Innenstadt, or the city center, and we have just sized up the heat pump for different capacities or heat pump fractions. And we can see that as we are increasing the size of the heat pump, also the levelized cost of heat slightly increases. And this is mostly due to the different capacity factors, which have a direct influence on the levelized cost of heat of the heat pump, and they can increase the levelized cost of the heat pump up to 18%. And as we can see that the heat pump works more efficiently in the region of around 0.7 or 0.8, which means that the heat pump should work 80 or 70% of the time, of the maximum time, of course. And in the next step, we have conducted some sensitivity analysis to see which is the most influential factor on the levelized cost of heat. And based on the sensitivity analysis, we can see that except the capacity factor, which was mentioned before, also the electricity price and the COP are the most inflation factors. And because of that, we have a closer look on the electricity prices and the COP as well. And the problem was not actually the higher investment or the conservative investment cost of around 1,500 euros per kilowatt. So in the next step, Jens already talked about this, about the cost structure of the electricity price in Germany. As we can see that in our case, around 30% of the electricity price is due to the generation costs. The remaining is based on a different taxes, like the surcharge for the renewable energy, other surcharges, concessions fee, billing and metering, network cost, and so on, which sums up and gives us the price of around 176 euros per megawatt hour. And then on the other hand, we can see that there are possible reduction under certain laws. These reductions can be applied for energy-intensive industries, and if the utility can use these tax reductions as well, the positive influence of the lower electricity price due to different taxations can lead up to 40% lower levelized cost of heat. In the next step, we have analyzed the COP more into the details. As mentioned before, we are in this graphic. We are on the right side, actually, in the temperature levels of around 80 degrees Celsius, and based on the different heat sources, we can see that heat sources temperatures. We can see that COP in the current district heating network can vary from 3 to up to 4. And in order to increase the COP, we have to make the transition to low temperature district heating networks. That will have an additional positive influence on the cost of heat of the heat pump. So how to improve the cost effectiveness? First, a proper planning, also that will consider the reduced heat demand to the better building insulation have to be considered, and higher capacity factors can improve the heat pump cost effectiveness. Then by completing the transition to low temperature district heating networks, we will further, let's say, close the gap between the existing coal-fired CHP plant and the heat pump price. And by lowering or considering certain investment costs and a certain tax reduction, we can actually reach the same or similar level as the existing coal-fired CHP power plant. So to conclude at the end, the electricity price plays a major role. With the current average price ratio between natural gas and electricity that in certain cases can go up to 3.8, there's actually no business case for heat pumps because at least the COP in that case should be much higher in order to compensate the price of the electricity. Then higher capacity factors should be considered as well. So in our opinion, the heat pump should work as much as possible instead of working as a peak shaver maybe, and also should consider the future demand reduction due to the thermal renovation. Of course, a very important factor is the transition to the fourth generation district heating networks that will have a positive influence on the heat pump efficiency, and the competition of the existing coal-fired CHP power plants, of course, it's one of the largest barriers right now. And in our opinion, the policies should focus more on operational costs and less maybe on the capital costs. So I would like to thank you for your attention, and for many other results you can visit the Progress Kit website, where we have actually considered the integration of many different renewable energy sources into the several district heating networks in Europe. So, thank you.
Thank you very much. Again, I will just ask if there is anybody listening that has an immediate question for FTIM. Otherwise, there will be a chance, as mentioned at the end. Yes, we have actually a question from Andre. Have you considered a sensitivity analysis with lower investment costs?
Yes, we have considered a sensitivity analysis, but as mentioned before, the influence of the electricity price and the COP plays a much, let's say, larger role in this case. And because of that, we actually focus more on how to improve, let's say, or how to reduce the electricity price, what are the options about it, and also how can the COP be increased of the heat pump. So in our opinion, even though we have assumed a much higher investment cost, in our opinion, even if we reduce them based on the sensitivity analysis, they won't give us the proper or the expected results, or we're not gonna make the heat pump competitive just by reducing the investment costs. So this is definitely not enough.
Yes, I thought it was very interesting, your focus on operational costs as one of the more important factors to look at. I'd also like to ask at what COP then the heat pump would be competitive based on current electricity prices. I think you said that would influence the business case potential a lot.
Yes, so in a range of between 7 and 9 for the COP, even for the current prices, the heat pump, current electricity prices, the heat pump will be competitive. But in order to reach this COP, of course, we will have to have a different heat source. Maybe use some industrial heat source which was not presented in the case of Herten, but in certain different cases where the industrial heat source can be used. to drive the heat pump. In that case, we can reach these COP values, and even more important are the working temperatures of the district heating network. With such a high district heating working temperatures, actually we cannot reach a COP values of around 7 or 8, so that we can make the heat pump more competitive.
Okay, thank you very much for those answers. And I hope that we can return to the topic of CHPs in the Q&A at the end, seeing as we have had two very interesting presentations related to that topic. But we have a couple more of speakers who would like to have the chance to talk about their presentations. So we have some new directions now. Our next speaker is Jay Hennessy. After working as a software engineer for many years, Jay then pursued a master's degree in renewable energy and the built environment. In the years since, he has contributed to the Swedish Bioenergy Association's International magazine and conducted research on life cycle analysis for the University of Gävle. Jay now works as an industrial PhD student at the RISE Research Institutes of Sweden in the Energy and Circular Economy Unit in collaboration with the RISB Research School. Jay, the floor is yours.
Thank you very much, Sarah. Hello, everyone. Yes, as mentioned, I work for RISE. I'm a PhD student also at Mälardalen University. And I'll talk to you about the future of thermal grids, or that is future district heating and cooling networks, and some possible interactions with other energy grids. Just to give some context, the International Energy Agency has forecast that between 2014 and 2020, the renewable sources of electricity will grow by 30%. And this means an increase of largely uncontrollable volatile sources of electricity, mostly from wind and solar PV. This volatility of supply can translate into volatility of the price. Here we see a graph from the North European Power Perspectives organization, where they have modeled the standard deviation of the electricity market price. They have price for the 2015 and a forecast for 2030. And here we see Finland, which is actually fairly representative of all the Nordic countries, being better protected from this price volatility due to the large hydropower reserves. But in other Northern European countries, here Germany, Poland and France, this standard deviation of electricity price increases from around 10 euros per megawatt hour in 2015 to over 100 euros per megawatt hour in 2030. So we need to find ways to absorb these energy fluctuations. A thermal grid is a concept based on traditional district heating and cooling, but in part provides additional services beyond just heating buildings, such as heat for producing food, here we see in the new demands area, and for societal functions such as melting of snow and ice. And also we see the introduction of so-called prosumers, consumers of heat, who are also exporting heat that they have produced themselves into the grid, presumably selling it. Compared to district heating and cooling, a thermal grid can be considered more generally as an energy storage and transfer system. And importantly, it will be coupled more to other smart energy grids. Here we see the electricity grid and the gas grid represented, so that the whole system can be used to efficiently manage the supply and demand of energy in different forms. We can see here in this diagram already some coupling points, and Jens and Andre have talked about heat to power. We wanted to, and in this example we have electricity being imported to produce heat in electrical boilers, in heat pumps for heat and district heating, and in the other direction we have heat being exported to the grid from combined heat and power plants. So there are some coupling points. We wanted to look at other potential coupling points, and in particular to focus on heat to power, so taking heat from district heating to produce electricity. We compared some candidate technologies, and one interesting case was recent innovations in organic Rankine cycle technology. So just to give you a brief overview of the organic Rankine cycle, it produces electricity based on the temperature difference between the hot circuit and the cold circuit. It uses an organic fluid with a high molecular mass, making the turbine efficient, and a boiling point lower than that of water, which allows us to recover heat from lower temperature sources. And recent innovations have given a higher level of efficiency from these modules for lower temperature sources. So we obtained data from 3 vendors of organic Rankine cycle, or ORC, modules, and calculated the levelized cost of electricity. So that is the net present unit cost of electricity over the lifetime of the equipment. So here we see the cost of electricity produced by the 3 vendors' modules. In green, we have the price from a heat source of 80 degrees, and in red, the price from a heat source of 120. And in both cases, the heat sink temperature is 20 degrees. And for each of these 3 vendors, we've also calculated the price using where the heat is used for different amounts of time in the year. So in the top group, the heat use is 75%, or 9 months of the year. In the middle, 11 months, and at the bottom, almost a full year, but minus 48 hours for the maintenance schedule of the organic Rankine cycle modules. And the key result here is that of the 3 vendors we looked at, vendor 1 consistently had the lowest cost. And if we take the most pessimistic calculation for vendor 1, that is with an 80-degree heat source temperature and an annual usage of 75%, we get a levelized cost of 69 euros per megawatt hour, or 6.9 euro cents per kilowatt hour. We then went on to do a sensitivity analysis just for this best performing vendor 1, in this case with a slightly lower heat sink temperature of 15 degrees C. And what we see here is an increase or decrease relatively in the levelized cost of electricity compared to the baseline. So the baseline is here at 0 in black. The key result here is that the installation cost, which is in blue, and the annual usage are the most influential factors affecting the levelized cost. The baseline uses the manufacturer's data to calculate the installed cost, but the installation is, of course, very site-specific and can be higher. And so this blue line shows the additional cost as a percentage of the basic cost. In other words, 100% at the far right there is effectively a doubling of the manufacturer's data for the installed cost. In red, the annual usage below 50% gives a sharp increase in the levelized cost of electricity. So the amount that these devices are used is important. The biggest constraint for this technology is the temperature of the thermal grids, or district heating. And the majority of district heating, of course, in Europe is 3rd generation, so generally below 100 degrees Celsius. With this particular technology, most low temperature organic Rankine cycles modules are optimized for 120 degrees. But those innovative vendors that we were considering are optimized for 90. The research for this particular study is ongoing. The next stage is to test against actual network temperatures to calculate the levelized cost based on those temperatures, and to establish under what scenarios this technology could be economically feasible now or in the future. And it's important to say that it's not just the heat source temperature that's important. The heat sink temperature is also as important, if not more important, affecting the levelized cost. And of course, this is largely, or to some extent, due to what those sources could be for the heat sink, whether it's from river water or lakes or using heat cooling, and therefore a need for additional equipment. So we see some potential uses for this as backup electrical power when the electrical grid fails, as providing balancing power to the electrical network. These newer devices have a ramp-up time of less than a minute, and as a source of distributed generation of electricity. These particular models were around 100 to 150 kilowatt outputs. So those were some of the first results we've had looking at one technology for increasing the coupling points between these energy domains. And I come back to this slide to show that here, although we have individual lines coupling the thermal grid to the electricity grid and the gas grid, of course, these coupling points are not only in one place, and an example is in renewable sources, electricity being used in heat pumps to recover waste heat from, for example, sewage, as identified by Andre as being a key source of waste heat. And in the future, we expect these coupling points to increase in number as the need for flexible energy systems increases, as a result of our increase in renewable sources of energy, as we saw at the very beginning. So the different domains and technologies have different time constants. For example, the electricity grid is on the scale of seconds. So it's an interesting feature of thermal grids that they are on the scale more of hours or longer without storage, but with storage can be on the scale of days or much more. So that was a brief presentation of the future role of thermal grids in a more integrated energy system. At RISE, we have a number of ongoing projects regarding integrating district heating and other energy systems. And this is an area of research that is growing quite rapidly globally. So thank you very much.
Thank you very much, Jay. Again, I'll just ask our guests if they have anything they would like to ask Jay before we move on to our next speakers and the final Q&A, where you will get another chance. But I personally would just like to follow up on, you mentioned that you have a lot going on at RISE. And are you working on any practical applications in terms of future thermal grids? It was very exciting, the presentation we got from you today, but it still seemed to be in sort of quite pilot stages.
Thank you, Sarah. Yeah, this particular study is at an early stage, but we do have some projects ongoing. I'm not personally involved in them right now, but we have a 5-year initiative called Symphonia, which is taking a couple of mid-sized European cities. And with regards to the integration of the different energy domains, it's looking at optimizing and making more efficient those existing district heating networks. In one case, using a hybrid hydrogen-methane backup system, for example. In another case, integrating solar energy and biogas gasification. We have another project actually based very close to you in Gothenburg, in Johanna Bay, on the Chalmers campus. And there it's a local energy system with an exchange of energy between buildings and production and storage. And an important aspect there is the integration and co-optimization of the electrical power system with district heating and cooling. And in that case, it's facilitated through a kind of a local marketplace where we have software agents placing bids on a local market. So these are a couple of case studies, one really quite concrete, and the other, you could say, in a more testing phase of a new type of market tool.
Thank you for that. And we can say that the market tool based in Gothenburg that you mentioned there, that project has signed on as a Celsius City supporter as well. So that means all of you listening with access to our toolbox can read a little bit more about it there and follow it as it develops. Thank you very much for that, Jay. We will now move on to our final speakers of the day, who are two experts from Skanska. Håkan Andersson holds a master's in civil engineering and works as a senior advisor at Skanska. And Magnus Karlström is TES program manager at Skanska and holds a master's in industrial engineering and management. Both have a lengthy professional experience in the field of energy efficiency. Welcome to you both. The floor is yours.
Thank you very much. As mentioned, my name is Magnus. I'm here together with my colleague Håkan. And we will talk about a new Skanska product that we think has a great potential linked to basically what we've been talking about today. The innovation that we're going to talk about is based on a collaborative work that we've done within Skanska during the past 10 years. Approximately 80 people have been involved in a way to try to solve as one of the greatest challenges that we have today, which is the challenge of storing energy. And the lead inventor and designer is named Hans Pilero and is working for Skanska. So what is it that we're talking about? Well, in essence, we're talking about a really big thermos that can store energy underground in a high temperature thermal energy solution. It's been stored both in combination of heat and cold in both water and rock. It's based on the sort of physical principle of that hot water is floating on cold water, which create a natural circulation in the storage. And based on the fact of the rock's insulation capabilities, we have relatively minor energy losses in this storage. In order to work in an optimal way, we have to combine and link the storage to a district heating and cooling system, which enables both storage short-term in terms of hours and also storage from a yearly seasonal perspective. It's a flexible and product, so it's very much adaptable to the need of the specific district and heating cooling system in which we would like to connect this product. And from a Skanska perspective, we have worked a lot to make this a patented product, and currently we have patents pending and patents approved in more than 30 countries. Some quick facts. We talked about this being a scalable product. So, for example, the seasonal storage capacity varies from 50 to 500 gigawatts per year, based on the version 7 that we're working on right now. But the fact is that we can turn over the heat in the storage about from 1 to 6 times, giving the turnover energy in the range of 300 to 1500 gigawatts per year, which is quite a substantial amount of energy. The TS storage is placed approximately 100 below ground level and linked, as I said, linked to a district heating and cooling system. And just to get a feel for how big it is, the diameter ranges from 200 to 600 meters, and the height of the storage is close to 300 meters, which can be equivalent to the Eiffel Tower. Just to give flavor for the investment level, we think that such a storage system with a seasonal capacity of 250 gigawatts per year will cost about 350 million euros. So how can TES contribute to the development of the society? I mean, first of all, it's a way of creating more efficient energy systems. It can also be a great benefit to the climate due to the fact that we can now reduce the carbon and other type of emissions, since we're able to take different type of energy sources and keep it and store it to when it's needed. And also the urban development part, I think, is very important, especially from a Skanska being a construction company. it's a mean of replacing old production CHP units, for example, by underground storage unit, which now can help transform the urban area in question. So a little more of how this can work in a district cooling system, and how we can sort of how the TS product can help them become more green. First of all, we can cut power spikes and move that energy from a time of sort of surplus to a time of need. And we can also increase the amount of waste heat into these systems. And we are also enabled to combine the renewable energy sources into these systems. For example, power to heat, but also other types of sources. So in some way you can say that the TS is future-proofed by itself, since it can use energy from any type of source. We talked about heat pumps, both from sewage heat pumps that was mentioned earlier today. Power to heat, we can link it to solar panels, process industries, data centers, or whatever energy source that are out there today. So let's move out a little bit and look at the big picture. We're coming from a historical perspective where we basically have been very dependent on the fossil fuels. And one of the benefits with fossil fuels is, of course, that we can turn them on and off basically when needed in order to match demand and supply. In the future, we are moving towards more renewable energy sources like solar, wind, wave, etc. And by nature, these sources are intermittent, well, if you exclude hydropower. So in order to be able to balance energy demand and supply, we will need some form of storage. And it's where TS can come in and contribute as part of the solution in achieving a fossil fuel free energy system going forward. If we look at the market potential, the market potential for this is globally. But if we look more specifically into Europe, where we have quite a substantial amount of district heating systems, there is a potential in basically all of these systems to have some type of storage. Depending, of course, on the size and the characteristics of each system, the size and the type of storage will, of course, vary. But we have legislative points to take into consideration here. For example, within the European community, energy companies are legally required to increase energy efficiency and also take advantage of waste and surplus energies from industries. And this is where one of the big challenges, how to do that in an optimal way. I think also one of the interesting things to mention is that in a sort of bigger study in Europe, talk about that 50% of the total energy need within Europe is linked to the heat area. And basically we have excess heat or waste heat that can cover all that need from a European perspective. And we're not really taking advantage of that possibility today. Also, we see we are sort of expect the district heating to grow over time, and partly is linked to the heavy investment that we see in renewable energy and the German Energiewende, because in order to take advantage of that heat, that electricity and energy that's being produced, we have to have some way of absorbing all that energy. And we think that the district heating system is one way of managing that surplus. So we think that the potential is great, and basically every large city with a district heating system, there is a need for some type of storage system, and that could very well be a TS facility. So where are we right now? Right now we are working with a number of customers, analyzing how the TS product can fit into their system. The product itself is more or less complete, but we need to sort of adapt it to each specific case. We have ongoing, as I mentioned before, ongoing applications for the patent worldwide. And the next step for us is to find a place and a customer together that we can build a demonstration facility with in Sweden. But why Sweden? Well, for us, Skanska is sort of the home base for us is Sweden, and the majority of our partners that we work with are also based in Sweden. There are also a number of well-developed district heating and cooling systems here. So from that perspective, Skanska feels it not quite natural to start here. But if there is a possibility elsewhere, of course, we're open for that as well. So to sum up, Skanska has developed a new product for storing energy, TES. We think it's quite a great innovation based on the skills that we have within Skanska and also with our external partners. We think the TES meets the current need in the market, both the market within district heating and cooling system, but also overall energy market with the increased amount of renewable energy sources. So I think, or we think, Skanska thinks that this is a great product that does not only have a great potential for cities and regions to improve the sustainability area, but it's also a product that we can talk about with our grandchildren with pride. Thank you.
Thank you very much. We will shortly go over to the Q&A, but first of all, I would just like to say thank you for coming and presenting this very important and interesting development. And I'm just wondering, have you had what kind of initial response have you had?
Well, especially when we talk to the political area, the response has been very, very positive, because this is really one of the means to sort of transform the energy systems towards fossil fuel free based solution. But also within the district heating system community, the response overall is very positive. To some extent, we have received a little bit of challenges because we are entering an arena where sort of it's looking outside of the Skanska core. So there's a little bit of the tension between the knowledge that we bring to the table and the existing incumbent companies that feel that they should probably have brought this idea up rather than us.
Okay, interesting. Well, I'm happy to hear that you're receiving such positive response from most stakeholders anyway, and we certainly hope that this technology will be rolled out and useful in the future. I'll now open the floor up to our participants for an open Q&A to ask any or all of our presenters, and I'll also remind our presenters, feel free to ask questions of each other as well. I feel like each of you has sort of presented a very interesting and different piece of the puzzle as we go towards integrated systems, incorporating renewable energy sources, waste heat sources into not only our district energy systems, but also looking at incorporating power and electricity as well. We have a few questions coming in at the moment in the chat. And just keep them coming as well. We can take them one after the other. So we have a question from our guest from Telia. Could you tell us, directed at Skanska, I'm assuming, could you tell us a little bit more about the TES and how it works, the size of the thermos, the temperature decrease over time?
Well, I can try at least. Basically, it's an underground storage that we talked about, and based on the season, we heat it up, inputting hot water into the storage during the summertime, where we have low cost for energy, and then the temperature, as water, we talked about the basic physical principle, hot water floats on cold water. The temperature in the storage varies from 4 degrees at the bottom up to 95 degrees at the top. And there's a number of areas where the temperature drops in certain levels. So we will have, when the storage is completely heated, it will be, the majority will be hot temperature, and there will be a smaller area with temperatures in between like 20 and 60 degrees, and then a smaller area at the bottom with the cold temperatures like 4 degrees. And the size of the thermals, we talked about that a little bit. They can vary from about 200 to 600 meters diameters, and it's approximately 200 meters high, and it's located approximately 100 meters below the surface of ground surface. You talked about the temperature decrease over time. In our initial analysis here, we talked about the losses of approximately 5 to 10% over how much did you put into the storage versus how much you can take out over a year, basically. So the insulation effect of the rock is very, very well. It works very well. So I hope that answers the question.
Thank you very much for that answer. And I will also and we've got a thumbs up from Telia there. I've noticed a few questions have also come in the chat from our speakers. Speakers, if you would like to ask a question to each other, you are free to unmute your microphones and ask it directly. So, for example, Jay, you had a question for Håkan and Magnus?
Yes, thanks. It was really regarding the cost of this solution. Obviously, it's a very, very large storage. What are the most important aspects for making it cost competitive compared to, that alone, basically?
Well, we're looking at a number of things here. First of all, we are looking at how we can be more cost efficient in actually building these type of storage. So we're working right now with a number of partners to see how we can optimize the cost for the construction part. A second area which is very important here is the turnover of the energy stored in the T storage over the year. So if we can sort of drive down the investment part a little bit, and also optimize sort of how you use the storage over the year. With those two things in place, we definitely think this can be a cost-efficient way of storing energy.
I can say another thing. When the storage is charged, it's about 100 or in 50 meters with 99 degrees. So you have a very big volume of 99 degrees. And then a little small area that go from 99 to plus 8 degrees or plus 4 degrees in the bottom. So we have a very, very big volume of hot water.
Thank you. And is how small can this solution go? I mean, you're looking at very large areas. Is it still feasible on a smaller scale?
From a technical perspective, the scale is not the problem. It's the efficiency problem that comes with a smaller scale. You have, you will have a certain sort of process part, the machine room, and all those kind of components will be there, and you can sort of not scale that down to have the availability that you need if you sort of scale down the actual storage area underground. So there is a sort of the cost of storage will be reduced, and the losses will be reduced with the size of the storage. So I think that's an important part also to keep in mind.
When we discuss with the customers, we compare investigations of storage with another CHP investment. So you can combine with a very big CHP investment to compare with the TS storage.
Yeah. In some areas, basically a TS storage can replace a new investment in a CHP plant. And as you all know, investments in CHP plants are quite substantial as well. So you have to really think about how you can use this type of solution in a district heating and cooling system.
I can also say we have very big heat pumps in the storage, internal heat pumps in the storage. It looks very, very nice to see how you have researches and so on in heat pumps. So we need the heat pumps inside storage.
Thank you for those good answers.
Yes, and thank you for the question as well. I think really one of the special things that we've seen today is really how interconnected everything is, how we can use heat pumps in relation to storage, how we can have heat to power, power to heat. And we have such a fantastic combination of research experts and more practically oriented experts in our panel today. So just before we round off for the day, I would like to ask all of you, what needs to happen now? We've heard we've heard that CHP is ready, that large-scale heat pumps are ready. But we've also heard some more pioneering technology that needs to be tested a little bit further before it will be rolled out. So I want to ask, what are the next steps? And relatedly, how can different types of actors, help each other to further this rollout? So this is a question to the whole panel.
I can
Go
start,
ahead.
and
Yeah.
I can say that from my perspective, I think we need to first see a change in the policies, in the institutions, in the way we see the heating sector overall, and understand that the heating sector is not a sector on its own, nor the electricity sector. And these ones, they need to be integrated so we can actually achieve what we want on reducing the CO2 emissions in the future. So from my perspective, it's not a technological barrier. It's more of a mindset barrier that still keeps us in the same bubble that we cannot integrate more renewables, we cannot make too many changes. So I think the change has to come in the institutions, in the policies, and that will allow us to integrate more power to heat solutions and all the other solutions mentioned in this webinar.
I can follow on from that, perhaps, to say that we know that there will be more renewable energy sources, and that it will be necessary to have better integration between the energy domains. And part of achieving that is also in what, as Andrei says, about a mindset of working together between these different domains better. And there are initiatives going on regarding this. Both Andrei and myself, and perhaps others here, are involved in an International Energy Agency annex looking at hybrid energy systems. These things are important to facilitate this transition to a renewable energy system.
Thank you. Would any of the other panelists like to contribute? Oh, and we have one last question coming in the chat as well. You can see, so if I can keep you all online for a second. But I think it's a very important point about this mindset barrier. I think we're finding this time and time again that our technological solutions are often coming, but it's the social institutions that cause some of the largest barriers. And that's certainly one of the things that we in Celsius have been trying to overcome by bringing actors together and working together on influencing market actors and policy makers. So we have a last question here from Barbara. Is it better in existing cities to renovate buildings and put in individual heat pumps rather than putting in a new district heating network? Would any of the panel like to address that question?
I have a short answer for that, and
Yes.
that is no. No, I don't. Individual heat pumps are not the solutions. The investment cost will be too high, and there wouldn't make any sense to have individual heat pumps, at least in urban areas.
Collective solutions, that's what we like to hear. All right. Oh, sorry.
I would also add something to the question. I would think it also comes, or it depends on the framework of the city, but yeah, also on the. What I also want to say is actually you can also renovate the buildings and put a new DH network in it. So I think that would be the best solution for the question.
Mm-hmm.
So,
Fantastic,
yeah.
and a very important point as well. That DH networks are not static; they can be extended. Thank you very much to all of our presenters. I think that's about all we have time for today. I'd like to thank our participants for contributing to the Q&A and dialogue at the end and for listening so attentively. And I'd also like to extend a very big thank you to our presenters for their excellent and varied presentations on this important issue.